Okay, so any questions up to here? I mean, we are technically speaking, we are not doing such complicated mathematics. We just have we already know our differential equation. So we obtain the equation, we obtain an approximate solution to our equation. The most important thing is how do you interpret the results. So we had in these systems, we started with a system in an A state, and we are looking for the transition into a B state. And now we started looking at an atom in an external time-dependent electric field, uniform electric field. Now, the kind of questions that we would like to discuss, the phenomena that we would like to discuss is, for example, if we have an atom, we know that if you shine the light of a suitable frequency, we are able to excite them. So that is what we call absorption. And then if you just let them stay there for some time, then we know that they decay eventually. That is spontaneous emission. And furthermore, in lasers, we also know that there is this phenomena called the stimulated emission. Now, in stimulated emission, kind of our derivation up to here, in quantum mechanics at least, is able to describe the stimulated emission and absorption. Because there is the external field which causes these transitions between the states. Now, the spontaneous emission is kind of more complicated because in the spontaneous emission, there is nothing external. So you just leave the atom over there, and it just, after some time, it de-excites itself. Now, then, of course, there is a problem if the initial state was an energy eigenstate. Now, in these, when we have these external fields, we know that the unperturbed eigenstates are not the eigenstates of my system. So that's why we have these transitions between various states. But if there's no external field, and if the energy states are eigenstates, and we create a state in an atom in this energy eigenstate, so why does it de-excite itself? Why does it make a transition? Well, in this case, in a sense, yes. The reason why, not the collisions. I mean, you can just isolate it. Even if you take an atom, isolate it from anything else, everything else. Even with the technology of, let's say, 100 years from now, you isolate it completely. There is no collision, no thermal effects, nothing, etc. And if you have this excited atom, after some time, it will emit the excited. The vacuum fluctuations. Basically, everything will be interacting with vacuum fluctuations. I mean, you cannot isolate anything from them. So they will be always there, and since there are these vacuum fluctuations, there will always be some external field, let's say, quantum external field at least, even if we don't apply it, and which will cause our system to make transition between various levels. Now, let's continue with this stimulated emission and absorption. So now we have this system. If we take the ground state, then the ground state can only be excited into the 1,1,0 state. So these are just two systems. And then, well, we already have derived everything. So the probability that we will have a transition from the ground state, the probability of absorption will be equal to remember, this is basically our expression. And of course, in this case, VBA squared is basically, we have this P, BA, and E0 squared. So the absorption probability PA squared EA squared sine squared omega minus omega 0 t over 2 divided by omega minus omega 0 squared. Now remember, the reason why we have this PBA is that we had defined H prime as V times cosine omega t, which in this case, this is minus Q E0 Z cosine omega t. And this P is the matrix element of QZ.
So for absorption, V doesn't have to be equal to V0.
Now, if omega is not equal to omega 0, you can still have an absorption probability. It doesn't have to be exactly equal, but only if t is small enough. No, sorry. No. At a given time, yeah. But if t is large enough, okay, so for any t, there is a probability that omega need not be equal to omega 0. But if t is large enough, the probability of absorption, if omega is not equal to omega 0, will be small. Remember this graph, the absorption probability as a function of omega has this shape at any given t. And this length is proportional to 1 over t.
From the equation about absorption, I mean, sine of something that is periodic, and how do you say that it's decaying to the
Well, you see, okay, so what can we say? Let's suppose that we have this atom over there. We send it some electromagnetic wave of a frequency omega different than omega 0. It's a collection of many frequencies, let's say. And now we wait for, I don't know, 1 hour and see which frequency is absorbed. And we will see that the frequency that is absorbed the most is the one that's close to omega 0. The other ones, well, actually what's happening is the atom is getting excited and de-excited. So if we wait, let's say, 2 hours, of course there is a finite probability that if omega is, let's say, 2 omega 0, there's a probability that it will be absorbed. But in a very short amount of time, it will also be emitted. So at the end of the 2 hours, there won't be any photons of frequency 2 omega 0 that is absorbed. So whatever was absorbed, it was released also.
Isn't that also true for omega equals to omega 0? So what absorbed will be?
Not necessarily. It can stay there. So,
as long as we give the...
Yeah, I mean, we constantly give this electromagnetic, we shine our light, which has let's say, a continuous spectrum. Then, of course, it will be absorbing and emitting all the frequencies. But after a long amount of time, let's say, the net amount of absorption of frequency omega is equal to omega different than omega 0 will be 0. You're not convinced. Not convinced.
Yeah, this is like new. So.
Hmm? Now, one problem that's kind of causes this thing not to be intuitive is that we are picking up one particular process. Here, for example, we are looking at only on the absorption. We say that that is kind of the only possibility. So that's kind of what makes it so non-intuitive. Now let's look at one more thing. Now this is the absorption probability for one single frequency. Well, in general, we cannot create such a unique monochromatic beam. So we mainly have a distribution of frequencies in our beam. So what is actually physically measurable will be not this one. This is for a single frequency. We will have a distribution of frequencies. dW, this is the total probability of absorption. Now let's just make a change of variables. Now let's look at this integral. This will be equal to d omega, rho of omega plus omega 0, p ea squared e0 squared sine squared omega t over 2 divided by omega squared. Now we said that this function, if t is large enough, as a function of omega, is a very peaked function at omega equal to 0. Do you agree? Yeah, this function, we said this is basically the shape of the function. If t is large enough, so this first 0 will come very close to omega 0. So it is very peaked, only close to omega is equal to omega 0, and it's very small in other places. And we will also assume that this rho is just a smooth function, at least close to omega 0. So what that tells me that I can just set omega is equal to 0 in rho. So this will be, well, let me just, in fact, skip this part completely. So this function is peaked around omega is equal to omega 0. And rho is a smooth function around omega is equal to omega 0. So if you deviate omega from omega 0 by a small amount, this rho doesn't change much. So in all the regions where this integral receives its contribution, that is close to omega 0, rho is just a constant. So I can just take it out of the integral. So this is equal to rho of omega 0, this PBA squared E0 squared integral of dW sine squared omega minus omega 0 over 2 times t divided by omega minus omega 0 squared. Now I can make a change of variable. Let's just say that x is equal to omega minus omega 0 over 2 times t. So dW is equal to 2 over t times x dx. And since again the integral is non-zero only in the close vicinity of omega 0, I can just set the integral of omega from minus infinity to infinity, or 0 to infinity, whichever one you like. The value of the integral will not change. I'm just adding terms that are negligible.
Should change if you lose from 0 to infinity or minus infinity to
Why?
double.
No. You see, that function is this one.
Yeah, this
So whether you take it from 0 to infinity or minus infinity to infinity doesn't make any change. Now if you make that change, now let me see our integral. The absorption probability will be rho omega 0, the matrix element of this electric dipole, E0 squared times 2 over t over 2 squared, integral from minus infinity to infinity, dx sine squared x over x squared. This is just a number. Now let me look at the number. Okay, that number is pi. So the absorption probability will be, okay, these matrix elements 1 over 2 Ea squared rho omega 0 times pi times t. Or let me rewrite it in this form. This matrix element times 1 over 2 epsilon 0. Okay, this is not Ea, this is E0. E0 squared rho of omega 0 pi times t. Well, the absorption probability increases with time. That is kind of expected because the more you shine, the more absorption you will get. And the absorption probability per unit time, this is just a constant. Well, that's what you would also expect. And this is the energy density, 1 over 2 epsilon 0 E squared, times rho of omega 0. Well, in this expression, it's already kind of, the transition is only to the omega 0 state. So, because the only density, the reason is only the density in that frequency is what determines the absorption probability. Now, if you look at the emission probability per unit time, you will see that it is also exactly the same. The difference we have to do is, remember, in calculating the absorption probability, what we assumed was we started from the ground state, and initially all the system is in the ground state. The excited state has 0 probability, so that we set the initial values of our C parameters. Ca was 1, Cb was 0. Well, the only thing we have to change is, in this case, Cb would be 1 and Ca will be 0. Everything else will be exactly the same, so that will be just amount to the exchange in here. Now, both of this absorption and emission are due to the external field that we apply. So our external field causes my atom to be excited, or if it is excited, it causes it to be de-excited. This is why it is called a stimulated emission. There is an external stimulus which causes my atom to emit a photon. Now what we call a photon is, just like the harmonic oscillator, we can treat the electromagnetic wave as just a collection of photons, collection of energy packets, and the energy of each one of these packets is equal to h pi times its frequency. So that packet is what we call the photon. So in that description, these processes are just absorption of a photon and the emission of a photon. Well, we will not be dealing with quantum electrodynamics, at least not much, but just to give you an idea, remember how we wrote the electric field? We had said that the electric field, or let's say the potential, the potential that we included in our Lagrange Hamiltonian was minus q E0 or E dot R times cosine omega t. This is equal to minus q E dot R cosine omega t. This was over 2 e to power I omega t plus e to power minus I omega t. Now, what we call the second quantization is that what we do here is we just replace this thing, in a sense, by minus q. Well, let me remove these coefficients by suitable coefficients. That's some coefficients over there times a dagger e to power I omega t plus a e to power minus I omega t. Now, these A and A dagger operators are what we call the photon creation and annihilation operators. So basically what we are looking at here in this problem is we started with 0 photons and the 0, 0, 0 state. Now, let's say 1 photon, we are sending this photon. We have this 1 photon state, and we are in the ground state, and we are looking at the transition from this state to 0 photon and the 1, 1, 0 state. This is the stimulated absorption. And these A and A daggers, they just act on this part, not on the other part. And for this is absorption. And for the emission, we start with 0 phonons initially, and now we have the 1, 1, 0 state, the excited state, and then this gets de-excited into N gamma is equal to 1, 0, 0, 0 state. Just the opposite reaction. This is what we call the emission. And the energy packets corresponding to this frequency omega is what we call the photons. Well, no, this emission is not this one actually, but we start from 1. 1 to 2. Yeah. 1 to 2. We send the photon.
The other one is the 0 to 1. The other process here, I guess.
Now that is the spontaneous one. 0, 1, 1, 0 to N gamma 1, 0, 0, 0. Well, this one, this stimulated emission, is what causes the lasers to work. So you start with 1 photon. You have a collection of atoms in the excited state. Most of them should be in this one. You get a bunch of them in the excited state. You send 1 photon to 1 atom, so it emits 2. Then each one of them causes another atom to emit two more, and then you get this avalanche of photons of the same frequency, and furthermore, they turn out to be at the same phase. So that's why you have the laser is a coherent beam of photons. Now, if initially you don't have this excited state populated, well, let's say half of them are in the excited state, half of them are in the ground state. So what would happen is, let's say you send one photon, let's say it hits that one that is in the excited state, which emits two photons. Then these two, one of them will cause another atom to emit, but the other one will be absorbed. So you will end up having two photons only all the time. So you will not have this avalanche of photons. This is basically called I think it's called the population inversion. So usually if you just leave the atoms without disturbing them, they will just go to their ground state. So the population of atoms will be all in the ground state. Then you have to make sure that most of the population is in the excited state to make the laser work. So that's why you need to pump energy to the system. And when all of them get de-excited, the laser doesn't work anymore. So most of the time the lasers have this pulse. It's hard to get a continuous laser. If to get the continuous laser, you have to pump them continuously. Now the problem is spontaneous emission. Well, with field theory, okay, we can calculate the spontaneous emission. There's no problem with that. But without the field theory, I mean, there's a nice argument by Einstein. So let's see what that is. So we will assume, first of all, let's just assume that we have, first of all, we should assume that we have enough time. Now this, okay, so here we have one result. For the emission, and the absorption is also the same for the absorption of a photon by the atom. Now, we already took some kind of an average over the possible frequencies, but one thing is, I mean, here at least we take one photon, so there's one particular polarization, but in general, the photons that we have in this room, for example, they don't have a particular polarization. Secondly, they come from everywhere. So what we are trying to do is, let's say we don't use spontaneous emission. In that case, we cannot use the quantum mechanics to calculate the amplitude of spontaneous emission. So we have to use some other means. So what we will be doing is we will just look at the blackbody radiation. So let's just assume we have a system of atoms in thermal equilibrium with some electromagnetic wave. We know that the rho of omega 0 for such an electromagnetic wave. So what we will do is we will just look at how the numbers of the atoms in their ground state and in the excited state, they will be changing. So let's say Na is the number of atoms in the A state. Now, the rate of these things, so why do they change? Well, there's a probability that they just go spontaneously, if they are the excited state, they spontaneously emit a photon, or let's say the B. This is equal to minus A and B. So we had already seen that for one atom, the rate of the probability of the emission is just constant, or absorption is just constant, the rate of the per unit time. So in a unit time, the change in the number of the atoms in the excited state, let's say, it will decrease with the number. So if, let's say, if per second 1 out of 100 atoms spontaneously emits a photon, then out of 200 atoms, there will be twice as much. Out of 300 atoms, there will be 3 times as much. So it is just this statement over here.
Radyoaktifliğe benzer.
Radyoaktif dikeye benzer.
So the idea is the same. I mean, any transition, in fact, the rate of change per unit time will be constant, whether it's a radioactive transition or whether it's an electromagnetic transition. So per unit time, the probability of transition is a constant. If that is satisfied, then there will be this term. Plus, of course, there will be a probability that if there are, let's say, B atoms in the system already, they will make a transition to the A state with a certain probability. This is due to the, let's say, stimulated emission. And if there are A atoms in the system, well, the A atoms can increase the number of B atoms by stimulated absorption. So here we have these three phenomena that will change the number of B particles in my system. So I'm imagining I have this equilibrium system. Let's say, to start with, let's assume that we don't have an equilibrium system. Any system. I have a system of atoms in, let's say, in the B state. If I have a system of atoms in the B state, this which is the excited state, their number will change due to the three phenomena that we have, two phenomena that we have discussed, and the third one that we want to study now. There is spontaneous emission. So if per unit time per A% of the atoms emit spontaneously, they be getting de-excited. So per unit time, A times NB of them will just get de-excited. So that is how much the number NB will change per unit time. So dNB by dt has this minus. So because the spontaneous emission, we'll call the number of excited atoms to be lowered. So that's why we have this minus. Now the second probability is the A and B atoms in A and B states, they are in an electromagnetic field, so they are in equilibrium with an electromagnetic field, so there's an external field in the environment also. And this external field will cause my atoms to be excited and de-excited. So if I have NB atoms, and if each one of them gets emit due to this stimulated emission, and if that rate is, let's say, BAB, then the rate of change, the change in the number of B atoms per unit time is just the probability of transition per unit time times the number of B atoms. Again, this will contribute to a decrease in the number of B atoms, so we have that minus sign. And then finally, we have an A atoms in my system. Now the A atoms in my system, they can get excited by absorbing this external electromagnetic radiation and become an excited state. The probability of absorption, stimulated absorption, if we call that B, then the rate of change of the number of B atoms per unit time will be the number of A atoms times this probability. That will be the number of atoms that is excited. That will increase the number of atoms in my excited state. This will be true in general. Okay, any questions on this one?
Equation seems like the ones coming up with Markov chains.
Well, this is a Markov chain. So every step is kind of independent of the previous step. I mean, if you have an atom in the ground state, the probability that it will be excited will be independent of how you created it in the ground state in the first step. Okay, in equilibrium, This is equal to 0. Now let's look at the rate of change of the A atoms, the atoms in the ground state. So what do you think? Well, in this case, the A atoms can absorb. So that would reduce the number. So that will be minus, let's say, B, A, and A. And there is a probable that also the B excited atoms can get de-excited. Well, they can get de-excited due to the external fields. Or they can get de-excited due to spontaneous emission. And each de-excitation of the B atoms will increase the number of A atoms. Now this is kind of expected also because DNA plus NB. Now this should be 0. The total number doesn't change. If an atom gets, if Na changes by 1, then NB increases by 1. Now let's look at equilibrium. So we have this thing. Now let me cheat a bit. Okay, there is one factor that I forgot. You see, the rate of absorption or the rate of emission. We had seen that they are both proportional to the density of the radiation with frequency omega 0. So here we have rho omega 0, rho omega 0, rho omega 0, and rho omega 0. So basically we have, if you want to have stimulated emission or stimulated absorption, you should have first the atom that is ready to absorb or emit. The more you have those, the more probable, the more transitions will happen. Secondly, you should have the radiation. What are you absorbing? So it should also be there. So that's why these things are proportional to their product. And even when you combine these things, there is a finite probability that they will be absorbed, and there is a finite probability that they will not be absorbed. And the probability of absorption are these B coefficients. Now, in equilibrium, we know that the numbers are constant. Question?
Doesn't rho omega 0 come up inside the
Inside?
Does the expression B have omega 0 inside it?
It doesn't have rho omega 0 inside. It can depend on omega. We will see. Now, if the Na or the number of particles is constant, their time dependence is 0, so we can solve for rho of omega. So it just tells me that rho of omega 0, if we have a system in equilibrium, then rho of omega 0 should be B, BA times NA divided by BAB NB plus A. No, hold on. This is not over here. This is over here. BAB NB minus BA and A, or B. Well, let me see. This is equal to 0. So we have, yes, divided by B
Numerator should be
minus.
A and
Yes. No, this was true. B and B is the second term. It is plus. No, it becomes minus plus. Now it's correct. Okay. So, okay, let's correct here also. This is A over BBA plus minus BAB and B over NA. Now, did you take thermodynamics? Okay, so you're chemical. Okay, so you have already probably seen the Boltzmann factor. So basically it tells me that NA is proportional to e to the power minus beta EA, and NB is proportional to e to the power minus beta EB. You remember this? Do you know this? So it tells me that NB over NA this is equal to e to the power minus beta EB minus EA, which is NB over NA is equal to e to the power minus beta h bar omega 0. I also think so. Okay, so I'm setting this one equal to 0.
In the numerator there should be NB instead of NA.
Now in the numerator I should have A times NB. Okay. Okay, so what I do is I just move the first two terms to the other side. So BBA becomes positive, BAB becomes negative. So if I divide by NB everywhere, so I have here I have NA over NB. Right? So do you remember black body radiation? No. You haven't seen the Fermi-Dirac Bose-Einstein? You did. You did. You? No?
I just remember the
Okay, so we can come back to this discussion after you study a bit of black body radiation. Now the issue is, the idea of Einstein, I think I really liked it. You see, this is the distribution of radiation, the radiation spectrum. But if you have a system that is in equilibrium with electromagnetic radiation, the distribution is already known. It is fixed, independent of what kind of atoms you have, what kind of system it is in thermal equilibrium with. Whether it's atoms that can be excited or de-excited or any system, if you have an electromagnetic radiation that is in thermal equilibrium, then rho of omega 0 is given by the black body radiation. So we know rho of omega 0. That is one information we know. The second information is the Na and Nb. So we have these atoms that can be excited or de-excited, they are in thermal equilibrium. But if they are in thermal equilibrium, then the probability that they are in the A state is proportional to e to the power minus beta times the energy of the A state. So that is why NA is proportional to e to the power minus beta EA. And NB is proportional to e to the power minus beta EB. The temperature. Beta is 1 over the Boltzmann constant times the temperature. So we know Na over Nb. We know rho of omega. So we can just read A and B's. And if you read them, I mean, if you just put what rho omega is, rho omega 0 is independent of the atoms. So you can put in their value and compare it with the right-hand side. So it turns out that BAB is equal to BBA. Well, this is what we had already known. The stimulated emission and stimulated absorption probabilities are the same. And let me cheat again. A. Just keep on a moment. Whatever. There is the coefficients. They are proportional to the stimulated emission and absorption rates also. So at least it's a neat way of obtaining this spontaneous emission probabilities by just using this argument. And well, once you know study the black body radiation, it will be more exciting for you. Yes.
Hocam çok beğendim. Bir semiconductor'da ki yani stilin intrinsik şeye oranın Ewald seviyesiyle iyi şey farkına.
Well, the treatment is almost identical if you are familiar with the phonons in a condensed matter system, for example. Well, that's black body radiation. You have the Bose-Einstein distribution, so you see here, the exponent over here, it just becomes, it should be 1 over e to the power beta h bar omega 0 minus 1 is proportional to omega cubed times this 1. So this is 1 over e to the power beta h bar omega is what we call the Bose-Einstein distribution. Omega cube is just the energy density, or you might remember from the modern physics course that you have took, there is this ultraviolet catastrophe. So that is this omega cube. And if you just compare this rho of omega with what we obtained above here, you see that the BBA and BAB, they have to be equal. You see the coefficient of the exponential and the coefficient of the constant term are the same. Just a relative minus sign. And the proportionality constant is A. So that is how we can read the A. A is the amplitude for spontaneous emission. And in fact, you can even read what BABs are by just putting in the constants. And in fact, it just turns out to be equal to the stimulated emission or absorption. All those three things turn out to be equal. Now, this is kind of a nice derivation where you use your knowledge from various fields. We have the electromagnetic interactions, and then we have the statistical mechanics where we take this rho of omega 0. And these electromagnetic interactions where we calculate this BAB and BBA, and even before we showed that they were equal. And then by just relating it with some thermodynamic property, we obtain what A is. That is the amplitude probability for for spontaneous emission. Questions? They will kick us out. Okay, if you have questions, ask me outside.